All right, so we are going to go through 7.6 today. So, in that packet that I gave you the other day, this was one of the things that I kind of had at the beginning. I misplaced it. This is what you guys will be doing um, on Thursday of the second week to review for the second Canvas quiz. I may add a couple like word problems at the bottom where you can just do those on a separate sheet of paper. But we're going to go here today, and then your homework was also in that packet, and you can also access that on Canvas. All right, and so we are going to start by just doing a quick review of 7.3. I'm really only going to do this problem just so I can keep this video as short as possible. If you want to copy down the answers to these two, they'll still be on the note outline key that's posted on Canvas. But when we did 7.3, we talked about how you can't solve an exponential equation unless the bases are the same. And so we use what's called the property of equality to do that. And so what we would do here is we would say, all right, our base is 2, our base is 16. How can I get those to be the same? Well, I can rewrite 16 as 2 to the 4th power. So then that's 2 to the x, and that would be 4 times 2x plus 1. Now that my bases are the same, in order for these two sides to be equal, these exponents have to be the same. So it has to be 2 to a power equals 2 to the same power. So then to solve, I would just set the exponents equal to each other. So then that would be 8x plus 4. Move the 8 over, and then divide by -7. So that answer would be -4/7. I would need to keep that as a fraction because it is a repeating decimal. And so we do the same thing here and then the same thing here. However, it's just not realistic for everything to so nicely match up. So there needs to be another way to solve these equations. And that's why we've been practicing those properties the last couple of days. So our focus the last couple of days was that exponents and logs are inverses of each other. So we're going to use that idea to help us solve these equations over the next several days. And so if I'm looking at this equation, your first thing is always still going to be to compare the bases. It's going to be way easier to use exponents as opposed to logs. So if you can get the bases the same, especially when there's variables in both exponents, that's what you're going to want to do. And so when I look at this first one, I see 2 to the x equals 5. Right. Well, I can't rewrite 5 as 2 to a power. Oh, there we go. Okay, I cannot rewrite, come on, there we go, 5 as 2 to a power. So there's got to be another way. Now I could sit here and guess and check forever. Well, I know 2 squared is 4, so maybe this is like 2 to the 2.2-ish. That's pretty close. And then I could keep guessing and checking, but that is really going to be inefficient and time consuming. And so we started talking about how logs and exponents undo each other. So if I am looking at that exponent with a base of 2, and I'm looking for that exponent, if I take log base 2 of both sides, kind of like how you would take the square root if you were trying to undo a square. So log base 2 is an operation, like adding, subtracting, multiplying, dividing. I'm going to write this out kind of the long way. So now I have log base 2 of 2 to the x equals log base 2 of 5. So whatever the base of your exponent is, the inverse is going to be that log, because now these undo each other. And so that's going to leave me with x equals whatever this is. Now, because I couldn't rewrite 5 as 2 to a power right off the bat, that means we're going to have to use the change of base formula. Sorry, Julius. um, because I couldn't start off by rewriting that as 2 to a power. I'm not going to be able to do that here. So remember, the change of base is always in log base 10, so we can do it on our calculator, and it's always the ratio. Shh. My gosh, guys, I'm so sorry. The UPS man is at our house. My dog is going crazy. Julius, say hi. Hi. All right. And so now I can type that in my calculator. Log base 5, not log base 5, sorry. Log base 10 of 5 divided by log of 2. And then that will give us our answer. And so that when we run to the thousandth is going to be 2.322. And that's what our variable will be. All right, so I'm going to do the same thing here. So now I've got 7 to the 9x equals 15. Well, I cannot rewrite these two values with the same base. And so if I'm trying to get that variable, and right now it's the exponent with a base of 7, the inverse of that is going to be to take log base 7 of both sides. So now those will cancel each other out, leaving me with just 9x equals log base 7 of 15. So this is where your calculator is going to come into play here. We have to make sure we type that in carefully. So I still need to get this x by itself by dividing both sides by 9. But you want to make sure you evaluate that log first. So you don't necessarily have to write it out like that. If you, now that we've been doing this for a couple of days, you can just kind of do that as you see it. So I would do the log of 15 divided by the log of 7. That's how we apply the change of base property, right? Log base 10, the ratio of that over log base 10 of that. Okay, so that's what my numerator is. And now I'm going to divide that by 9. And so my answer here is going to be about 0.155. All right, so now we're going to start to get to some of the more complex equations. So with these first two, we just had our exponent, 7 to the 9x to the x. So now the rest of these we're going to look at, well, what do we do when other things are happening to that exponent? So in this one, I mean the 5 to the x. That's our exponent. In this one, that's just 3 to the negative x. That's the only thing that's being raised to the power. In this problem, the only thing that's being raised to the power is e. In this one, the only thing that's being raised to the power is e. So everything that we put a box around, we need to get by itself before we can take the log to undo the exponent. Okay, and so for this one, we use regular rules of solving equations. So I need to subtract 1 from both sides. That's going to give me 359. Now I've got my exponent by itself. So if I need to get this done, it's an exponent with a base of 5. The inverse of that is going to be to take log base 5 of both sides. So it's similar to taking the square root. So it's still an operation. Log base 5 is an operation, like adding, subtracting, multiplying, dividing. So now those cancel each other out, leaving me with log base 5 of 359. And then I'll use the change of base property. So that's the ratio log base 10 of 359. Make sure you close that parenthesis. That would have messed things up. Divided by log base 10 of 5. So that variable is going to be about 3.656. All right, so I want you to pause the video and try this one on your own. Just hear me out. Try it on your own first. All right, let's see how we did. Okay, so this is what we need to get by itself. Normal rules of solving equations apply. So the first thing I'm going to do is add 18 to both sides. So I've got 1/4 times 3 to the negative x equals 36. Well, right now, again, this is the only thing that's being raised to the power. So I need to get that by itself before I can take the log of each side. Right now, it's being multiplied by 1/4. So I need to divide both sides by 1/4, which is the same as if you thought of like undoing the fraction, multiplying by 4. That's the same thing. But what a lot of people will do is just multiply the 36 also by 1/4. Okay. Which if I had put a 4 here, I don't think anyone would have multiplied 36 by 4. Everyone would have divided. But because it's a fraction, people flip out. Okay. And so again, you either multiply by the reciprocal or just divide by the fraction itself. So 36 divided by 0.25 is 144. The same thing as 36 times 4. So now I've got 3 to the negative x equals 144. I've got my exponent by itself. I need to undo that. I need to figure out what this value of x is. So the inverse of an exponent with a base of 3 is a log with a base of 3. Whatever I take on one side, I have to do to the other. So now those cancel each other out, leaving me with negative x equals log base 3 of 144. And then I would just need to divide by -1. So the log of 144, doing change of base, log base 10 of 144 over log base 10 of 3 is positive. So I'm just going to go ahead and change that to a negative when I write my final answer in. So -4.524 is what you should have got as your answer. Okay. All right, so now this one we're going to approach the same way. I need to get this exponent by itself. Normal rules of solving equations apply. So I'm going to add 14 to both sides. 11 plus 14 is 25. And so now I need to get this e to the x by itself. That's the exponent. So we have e to the x. 25 over 3 is going to give me a repeating decimal. So leave it as an improper fraction so we can get as exact of an answer as possible. So now we think, all right, so I've got an exponent with a base of e. In all of these other ones, I used the log, the common log that had the same base. So exponent base 5, log base 5. Base 7, log base 7. Base 2, log base 2. Base 3, log base 3. So we think, well, what kind of log has a base of e? Well, that, my friends, is the natural log. So if I take the natural log of both sides, that will undo that. Now you can do the common log, but it's a lot messier to type in because you have to use a change of base. So it's just way easier to do natural log when it's base e, since that is what undoes it. So then that's going to be x equals the natural log of 25 over 3. Which is going to be about 2.12, and then that's just going to stay 0, so 2.12. Okay. All right, and so now this last one's going to be similar. So I'm going to add 7. Remember, this would be exponential decay. Since k is negatives, we're going to be getting back to writing some of our own equations in the word problems. And so make sure we remember kind of those characteristics. The 4 is not being raised to the power, just the e is. So I'm working on getting that by itself. So I'm going to divide by 4. And then I get 5. And now I can undo that exponent. So right now, if the base of the exponent is e, the natural log is what is going to undo that. So those cancel each other out, leaving us with negative 0.3 equals the natural log of 5. And then I would divide by negative 0.3 to undo that. So the natural log of 5, close the parentheses, divided by negative 0.3 is going to be about negative 5.365. And that would be my answer. So again, these are all just, our goal is to get the exponent by itself. Okay, so what a lot of people want to do here, just to kind of show you guys their stuff on the back here. So a lot of people will see something like this, and their eyes see 5x. So they'll divide by 5 and get x. Well, division undoes multiplication. This is not what's happening here. To solve any equation, you are always inverting, 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 right? So like when we did this one, we added to undo the subtraction. We divided to undo the multiplying. So if you get to this point and you're dividing by 5, you're not undoing the operation. A log undoes an exponent. And we'll learn tomorrow, well, no, not tomorrow, Wednesday, how an exponent undoes a log. They're inverses of each other. So please make sure this is a no. This will make me very sad. Okay. Make sure you're understanding what you're undoing. All right, so now if we look at this last word problem here, it says a certain element decays according to the formula P equals P sub 0 times e to the negative 1.2t, where t is in years. How long will it take for an element to decay to 1/2 of its original amount? So first we have to think back to, this is exponential continuous growth, because we've got that a value, or e value, not a value, the e to the k here. So a couple of review things about that. Remember, that is the general formula for an exponential growth that's growing continuously. So this value right here always tells us what we're either growing or decaying by. T is almost always going to be time. And then this is always our initial value. So in this problem, P sub 0 represents our initial amount, right? And that anytime you see that subscript of 0, that's what that means. What is it after 0 time has passed? This tells us that we are at 12% decay because it's negative. So it says, how long will it take for the element to decay to 1/2 of its original amount? Well, we don't really know what that initial amount is, but truly it doesn't matter what you put in your equation, because the relationship between these two should always be 1/2. So it doesn't matter whether you put 150 or 50 and 25 or 20 and 10, because no matter what, our first step is always going to be to divide that to get the exponent by itself. So you're always going to get 1/2. So I always just recommend making it easy. Make your initial value 100 when you don't know it. Okay, so if I make 100 my pretend initial amount, and I want to know how long it's going to take for it to decay to 1/2, then that's going to be 50. So just like in all of these other ones, now I'm solving for the amount of time. So similar equations to what we started off this unit doing, but now we never solved for this. We either solved for the initial value or the final value. Well, if I'm solving for the exponent, the inverse of an exponent, the only way I can undo that is using logs. So I need to get that exponent by itself. The 100 is not being raised to your power, just the e is. So I'm going to start by dividing both sides by 100, and you're going to get 0.5. Now my exponent is by itself. The base of the exponent is e. So the natural log is what will undo that. So then these cancel each other out. So now we have the natural log of 1/2 equals negative 0.12t. And now we can solve. So natural log of 1/2, close those parentheses, divided by negative 0.12 is about 5.8 years. Okay. Now that seems legitimate based on the question, right? If we're losing 12% every year, and we're looking at 5 years, half, that seems like a reasonable answer. We talked about reasonableness at the beginning, right? If you accidentally use a wrong growth factor and you get like a negative final amount, probably not right. If you're going from a $25,000 car after 12 years and your car is going to be worth $10, your growth factor is probably wrong. So always think back to the word problems. Does this answer seem reasonable? Okay. So we're going to do the same thing here. My final amount is just going to be 1/4 instead of 1/2. So if I start with 100 again, 1/4 of 100 is 25. And this is the same scenario. It doesn't matter what you make your initial value, because no matter what, your first step to get that exponent by itself is always going to be to divide. So you should always get 1/4 when you divide your initial value. So then now I can undo my exponent, take the natural log of each side. It's natural log of 1/4. And then I can solve. Natural log of 0.25 divided by negative 0.12 is about 11.6 years, which again seems reasonable to me. Okay. All right, so your homework tonight. I thought I had it. It was in that packet that I gave you. It's the 7.6. I thought I had it with me, but it's somewhere around here. You guys should see the state of my dining room right now. It's a mess. But is the 7.6 homework that was in the packet also can be accessed on Canvas. Just hop on Canvas conferences if you have questions.